Hi everyone, we're going to start with chapter 5 now, which is based on the normal probability distribution. Back in chapter 2, we looked at the normal curve and we determined that based on the empirical rule, there would be approximately 68% of the data under a normal curve that would fall within one standard deviation of the mean. So this is just going to kind of be review, which made that 34% and 34%. And then it determined that within two standard deviations of the mean, there's approximately 95% of the data. And we worked out to show that that was 13.5% and 13.5%. And then within three standard deviations of the mean, there was approximately 99.7% of the data. So that was another 2.35% and 2.35%, leaving 0.15% on each end. So this was mu plus 2 standard deviations, mu plus 3 standard deviations, and then mu minus 2 and mu minus 3. And we also talked about the fact that we could base the distance a data piece was from the mean on something called a z-score. And z was calculated as the data piece minus the mean over the standard deviation. And we determined that positive z-scores were above the mean. And negative z-scores were below the mean. And that's as far as we took everything with chapter 2. Well, now in chapter 5, we're going to get a little more specific on probabilities relative to z-scores. This is section 5.1. And we're going to be able to determine not only what a probability would be of being just 1, 2, or 3 standard deviations away from the mean, but 1.4 standard deviations away from the mean, or 3.6 standard deviations away from the mean. So we're not going to be keyholed into just the whole number values and getting approximate probabilities. The type of distribution we're going to be talking about in this chapter is the continuous distribution. When we did chapter 4 and we talked about an XP of X table, or we talked about binomial or geometric or Poisson problems, all of those were discrete distributions. They had a finite number of values. We could find the probability that X was equal to a number. That was discrete. Well, this is continuous. There are an infinite number of values X can take on in a continuous distribution. Because between every two numbers, there's another number. Between every two numbers, there's another number. We refer to this normal curve as being an asymptote because it's never going to touch the x-axis, it's going to approach it. You will not be able to find probability at a point. Because with this curve, probability is equal to area under the curve. And area is two-dimensional. So we need a width and a height. The height is the curve. The width is going to be a starting point and a stopping point. This distribution is just like the discrete in that the sum of all the probabilities has got to equal 1. And each of the probabilities that you will find will have to be a number between 0 and 1. So in this curve, the total area is equal to 1. When we talk about a portion of the curve, that'll be a part of the one, that part of 1, and therefore that will equal the probability. So let's look at some exact values that are different than the 1, 2, 3, -1, -2, -3, and look at the probabilities associated with those. To do that, we're going to look at the z-curve or the standard normal curve. The standard normal curve was established so that you could use, before calculators were around that would do all this for us, that you could use the standard normal z-table. And I'm going to show you how to find probabilities relative to the z-table, and then I'm also going to show you how to do it on your calculator. But the standard normal curve is the normal distribution with a mean of 0 and a standard deviation of 1. So that means the value in the center is 0. And then 1, 2, and 3 positive values going up. -1, -2, and -3 would be your z-scores, which would mean the number of standard deviations above or below the mean. Well, if I wanted to find the probability of having a z-score that is less than -1, based on the empirical rule, I can look back up here and see that less than -1 would be approximately 16%. But I want to be more exact. And so I'm going to use the z-table to show you how this is done. The z-table is a table of values before calculators were used that would allow you to find probability to the left of any z-score up to 2 decimal places for the z-score. And the probability is given to you in 4 decimal places. So if I scroll through this, and I will put this on Noodle, if I scroll through down to -1.00, then I can see that the answer is 0.1587. And that makes sense that it would be less than 0.5 because at 0, half of the graph would be shaded. But if I wanted to find the probability of being greater than some value, let's say greater than 2.4, and I would strongly encourage you to sketch a graph every time you do a problem, and you'll see me do that. So here's 2.4. If I wanted to go greater than 2.4 and use the table, I would find 2.4 in my table. Again, notice the shaded area is to the left of the line, and 2.4 would be 0.9918. Well, looking at this curve, you can tell that that is not 0.9918. It's a lot less than that, because not even half of the graph is shaded. Based on the fact that the numbers in the table are probability to the left of the line, that means that this area is 0.9918. So to get my answer, I would have to do 1 minus 0.9918, which would equal 0.0082. And again, both of those are using the Z table. The good part about this is that you don't always have to use the Z table. You could use your calculator. So I want to show you where to go to on your calculator so that you can calculate probabilities using the normal distribution. Just like finding probabilities for binomial and geometric and Poisson, you can go to second vars. Remember in binomial, geometric, and Poisson, you had the PDF and the CDF, which you do here, but we will never use normal PDF. Because remember, PDF is for probability at a point. That's for something that you will not do. That's for non-parametric statistics. So we are always only going to use normal CDF. Now what you'll see whenever I hit normal CDF is that your calculator, if you have a newer calculator, will ask you for the lower boundary, the upper boundary, the mean, and the standard deviation. Because that's what the normal CDF function asks for on the calculator. So on the calculator, you would go to second vars and choose normal CDF. And it is going to ask you to put in the lower boundary, the upper boundary, the mean, and the standard deviation. Well, because we're on the z-curve, our mean and our standard deviation are 0 and 1. So if I wanted to find the probability that z is less than -1, I need to know where that curve is going to stop. So that everybody is putting in the same numbers, the standard thing to do when using the far ends of the normal curve is to treat the negative end, which is negative infinity because that asymptote will approach the line but never reach it. We're going to use negative e to the 99th. If we're on the positive end, and that's our boundary because it's going to keep going to infinity on the upper end, we are going to use positive e to the 99th. So in this situation, if I were to draw the normal curve and shade the area that is less than a z-score of -1, I would use normal CDF. My lower boundary would be negative e to the 99th. My upper boundary would be -1. My mean, because it's talking about z-scores, is 0. And my standard deviation is 1. So looking at the calculator, I would put the negative sign in first. E to the 99th is right here above the natural log. So I would hit second natural log and it would bring up e raised to a power, and I would put 99, and you have to close the parentheses. And then my upper bound was -1. I already have in here 0 for my mean and 1 for my standard deviation. And when you hit paste, if you have an older calculator, this is the way you would type it in. Negative e to the 99th, comma, -1, comma, 0, comma, 1, close the parentheses. And when you hit enter, you get 0.1587 if you round. But notice you get a lot more decimal places for your probability. So I'm still getting the same answer I did earlier. Whoops. But it's much easier, and using the functions on your calculator will help you find any direction, any boundaries a lot quicker than trying to use the table. Let's go back and do the other one. Z is greater than 2.4. Again, I'm going to draw my curve. I know that 2.4 is up here. I know I'm going greater than, so I'm going to use normal CDF. 2.4 e to the 99th, 0, 1. So let's look at that on the calculator. Remember, second vars, we're going to choose number 2. My lower bound this time is 2.4. My upper bound is positive e to the 99th, so second natural log. 99, close the parentheses. 0 and 1. And I get 0.0082. Which is the same thing I got when I used the table. So that just shows you that whether you use the table or whether you use the calculator, you will get the same answer. To me, the calculator is just easier. So let me show you one more problem. If I wanted to find the probability that z was between two numbers, let's say between negative 1.36 and positive 2.1. So negative 1.36 is on the lower end. Positive 2.1 is on the upper end, and I would shade between them. So in this case, my lower bound and my upper bound are actually numbers. So negative 1.36 is the starting point. 2.1 is the ending point. 0, 1 are my mean and standard deviation. So I'm going to go again to second vars, choose number 2. My lower bound is negative 1.36. My upper bound is 2.1. My mean and standard deviation are the same. And I get 0.8952. So that kind of shows you where we're headed. We're going to be using the normal distribution curve for a lot of things from here on out. We know that the total area under the curve is equal to 1. The standard normal z-curve has a mean of 0 and a standard deviation of 1. And to find any of the probabilities, I need to draw it, shade it, so that I can tell what my lower bound are, my upper bound, and then my mean of 0, my standard deviation of 1. And that is the end of section 5.1.